Welcome to the GMAT Strategy Podcast. You're here because you believe there's a better way to study for the GMAT, and so do we. We created the GMAT strategy to maximize your results and minimize your effort so you can get to the fun parts about business school and life as quickly as possible. My name is Isaac Puglia, and I've been teaching GMAT classes and tutoring privately for the GMAT for almost a decade, and I've achieved a 99th percentile score on the GMAT and helped thousands of students get into the business schools of their choice. I'm excited to be a part of your MBA journey since we all at TGS think our world can benefit from the best possible business leaders that we can find. If this show is bringing you value, please share it with your friends and family who are studying so that together we can make this process as easy and as painless as it can possibly be. Let's go.
Welcome to lesson 19 of GMAT Math Basics. Today, let's talk about equations. We've arrived at a level of mathematical understanding that will allow us to explore slightly more complex topics, in this case, equations. Equations are really useful. We use them to predict how things are going to occur in the future, for example, with budgeting, credit scores, and loans. We use them to understand how the physical world works, for example, in the field of physics, and we use them to understand things as mundane as travel and commuting, for example, computing miles per gallon or the time a trip will take to complete. There's also quite a bit more, of course. They're used in many areas of business, not least of which would be calculating revenue, costs, profits, and losses. So it's very worth having a strong basic understanding of what equations are, how they're constructed, and how they're likely to appear on the GMAT. Because one important use of equations is creating challenging GMAT questions to test our reasoning skills. So let's begin with a short quiz so you can test yourself on this information in the future if that is helpful for you. The first question that we're going to answer today is, what is a variable? A second question we'll answer is, what is a coefficient? Then we'll answer, what is a term? We'll answer, what is an expression? Of course, we'll answer, what is an equation? And finally, we'll ask, how do you simplify equations? And we'll answer that as well. Here we go. In order to understand equations well enough to get a great GMAT quant score, we should begin with some definitions. Number one, what is a variable? A variable is a symbol, usually a letter, that represents a value that can change. This is why it's called a quote-unquote variable. It can vary. Variables are really useful because sometimes we don't know what a certain quantity will be. For example, in calculating revenue, we might be able to predict how much a unit will sell for because we're often setting the price as the proprietors of the business. But we may not know how many units we're going to sell. And if we wanted to set up a model that could predict revenue or simulate different types of revenue outcomes, it's really useful to have a tool that can help us do that. And variables are that tool, or at least they are one of the key concepts that allows those tools to operate. So we're using variables all the time, a lot of times without even knowing it, just by using devices and modern technology. Variables on the GMAT are usually depicted as letters. A, B, X, and Y are the most common, but technically any letter or symbol could be used. 99% of the time, though, the GMAT will express variables using letters. Many times, the exam will differentiate variables from written text by writing variables in italics, and that means the letters are slightly slanted to the right of the page. But they don't always do this, so you will need to be able to recognize variables when they appear in mathematical expressions. Consider a quick example. Let's say a GMAT question asks you for the value of x plus 5. Whether x is printed in italics or not, you're expected to know that x represents an unknown value, what's called a variable, that could theoretically be any number. If the exam asks you for the value of m plus 5, you'll be expected to know the same thing. M could theoretically be any number. Those are the basics of variables. Let's continue. What is a coefficient? Coefficients are numbers that multiply variables. sometimes divide. But because division could be expressed as multiplication by a fraction, I like to think of coefficients as numbers that multiply variables. It just keeps things simple. One way to express multiplication is using parentheses, and one way to express multiplication with parentheses is having no space between the number that's doing the multiplying and the parentheses itself. We've actually discussed this in lesson 2 of this GMAT Math Basics series. And if you're not sure what I'm talking about, now might be a good time to go back to lesson 2. We often extend this convention to variables. And what I mean by that is if you see a 3 written with no space in between it, and then the letter X, like right to the right of 3, again, with no space between it, that represents 3 times X. If it's helpful, you can imagine a set of parentheses surrounding the variable in those kinds of situations until you get used to the convention. In this case, 3 is often called the coefficient of X. It's going to be an important part of solving equations, which of course is a big part of the GMAT quant section. So really we just want you to understand this definition of what the exam means when it says the word coefficient, and then also how it's depicted visually so that you can recognize it if and when it shows up on your exam. Another quick example to hopefully drive this point home, something like 5 with a y right to the right of it with no space in between would represent 5 times whatever the value of y is. The most common way that that is described is just calling it 5y. And you'll want to know that when we say 5y, that means we're multiplying 5 times y, and 5 is the coefficient of y. Those are the basics of coefficients. Feel free to rewind that if you still don't feel 100% clear. And as always, feel free to reach out to us if you get stuck or have questions with this. We're at the GMAT strategy on current social channels. That brings us to the concept of terms. What is a term? A term can be a variable by itself, a number by itself, or a variable that is being multiplied or divided by a coefficient. I'll say that again. A term could be a variable by itself, a term could be a number by itself, or a term could be a variable that is being multiplied or divided by a coefficient. In general, a term does not involve addition or subtraction. There's definitely disagreement about this out there, but for the purposes of our discussion and for clarity, when I say term going forward, I mean a variable by itself, a number by itself, or a variable that's being multiplied or divided by a coefficient with no addition or subtraction going on in the situation. Again, pretty much anything that does not involve addition or subtraction could be defined as a term. Quick examples: 3x, or 3 times x, is a term. X over 4 is a term. X plus 4 is not a term. That's called an expression, which we'll get to in a moment. It's not a term because it involves addition. X plus 4 is not a term for the purposes of our discussions. Terms are important because of something called like terms. Like terms are terms that multiply or divide the same variable or variables. I'll give you some examples of this in a moment. Like terms are terms that multiply or divide the same variable or variables. For example, 3x and 5x are like terms because they are both multiplying the same variable, in this case, the variable x. Just to dive deeper into this concept of dividing the same variables, that would have to be a combination of variables. For example, 3xy and 5xy would be like terms because they both multiply the combination of variables xy. We'll get a little bit deeper into the intricacies of that in a moment. Similarly, 3x plus x over 4 are also like terms. Even though one is multiplying x and the other is dividing x, they are still multiplying and or dividing the same variable. Ergo, we consider them like terms. What are unlike terms, or terms that don't fit this definition? Unlike terms are terms that involve different variables. For example, 3x and 5y are unlike terms. Why do we even care about like terms? It's because like terms can be combined, and combining like terms is extremely useful when it comes to dealing with equations, especially complex ones like those you might see on test day. What does combining like terms mean? Well, you can add like terms. For example, 3x plus 5x is equal to 8x. That might not seem like a very big deal, but again, it will be very helpful later. And I'm just introducing the basic concept here. If that's confusing, think about having 3 apples and then getting 5 more apples. Now you would have 8 apples. You have 8 of all the same thing. You're combining similar items. But if you have 3 apples and 5 oranges, and you put them together, now you just have 3 apples plus 5 oranges. And you probably wouldn't think about them as a single unit. That's a decent real world analogy for how like and unlike terms work. You can also subtract like terms. It's very similar to adding. If you subtract 3x from 8x, you would get 5x. Again, this might seem trivial right now, but it's really helpful in a bit. It will be really helpful in a bit, excuse me, when we get to simplifying equations, which is a huge, huge deal on the quant section. Quick side note, multiplying and dividing like terms is really not as important of a concept because nothing very special happens when we multiply like and unlike terms. For example, 3x times 5x is 15x squared, which I think is pretty expected for most people. It's worth touching on, but it's not really worth diving deep on, and unless these concepts are just so foreign to you that you need to make some flashcards just to get familiar with the hardcore basics, which is fine. Many people start there and get great GMAT scores. Similarly, 3x divided by 5x would also be what most people expect, which is the x's just cancel out and you're left with 3 over 5. So again, it's worth touching on, but we're not going to spend a lot of time on it because that works pretty intuitively. This is what I've noticed after teaching people how to take this exam for many years at this point. In fact, you can often multiply unlike terms together. For example, 3x times 5y is just 15xy, or 15 times x times y. Again, that's not very unexpected. There aren't like a lot of rules that most people would be prone to breaking in that kind of situation. So it's really just worth mentioning in passing. If you want to memorize something helpful related to this, though, just remember that you can only add or subtract like terms, but you can multiply and divide any terms, whether they're like or unlike. If you wanted like a quick little summary of what's important there, that would be a good little flashcard or a good little note to make. One short final note about terms. Terms do include exponents, but in order to be like terms, the exponents need to be equal. For example, 5x squared plus 3x squared does equal 8x squared. So because the variable is taken to the same exponent, in this case 2, then they're considered like terms. But 5x squared plus 3x cubed cannot be combined without doing some clever factoring. So for now, just consider them unlike terms. We'll get to factoring and manipulating complex exponent expressions in the future. We'll just keep things simple for now. So good news here, that's pretty much everything you'll want to know about terms for the GMAT. This brings us naturally to the concept of expressions, which I mentioned moments ago. What is an expression? Expressions are combinations of numbers and terms that involve addition and subtraction. Some examples of expressions would be 3x plus 5y. 3x plus 5y is an expression. It's a combination of numbers and or terms, and they're being combined with addition and subtraction. 13x minus 17y times 4 is an expression. Expressions can be simple, they can be complicated, but generally, if you're combining terms with addition and or subtraction, you've got an expression. Expressions are mostly important so you understand the explanations of algebra during the study process. It's not something that has a ton of utility as a concept during the test itself. So let's continue. What is an equation? An equation is a statement that declares that two or more things are equal to each other. That might be just massively redundant and massively obvious, but it's worth touching on. For example, 7 equals 7 is technically an equation. Probably not a revelation, but if you didn't know that, thank goodness we're having this discussion right now. More commonly, though, you'll see equations like x equals 9, or more complex examples like x plus y equals 3z minus 4. What that's telling you is that the sum of x and y has the same value. as z times 3 minus 4. That's what the equation x plus y equals 3z minus 4 is telling you. It's telling you they have the same value. Why do we care about equations? Well, we already talked about how useful they are in real life. But the main reason we care about equations on the GMAT is that the GMAT loves equations. In fact, we could make the argument that every GMAT quant question involves equations. In practice, it's probably more like 80 or 90%, but either way, it's a major, major topic in the quant section. So it is very worth understanding the basics and also how you'll want to deal with them. So this brings us to a very important question. How do we simplify equations? Simplifying equations is a massively important concept because almost every equation that involves, almost every question that involves equations on the exam also involves simplifying those equations. Let me just say that again. Simplifying equations is a massively important concept because almost every question that involves equations on the exam also involves simplifying those equations. So when you see equations, you're probably going to be doing some simplification. Good news, there are only a few rules you'll want to know to be great at simplifying equations, and the rest is just practice. So let's jump right into those. Rule number 1 of simplifying equations: any operation that you do to one side of an equation should be performed on the other side of the equation as well. I'll say that again. Rule number 1 of simplifying equations is that any operation that you do to one side of an equation should be performed on the other side of the equation as well. This is sometimes called the golden rule of algebra, which is similar to the golden rule in life, which is treat others how you want to be treated. Do unto one side of the equation as you would do unto the other. So that's rule number 1 of equations. Rule number 2 is only add or subtract like terms. We've already discussed a little bit about like terms, but we're going to build on that concept here in a moment. Rule number 3 is that simplifying means eliminating as many terms as possible. So rule number 1, any operation that you do to one side of an equation should be performed on the other side of the equation as well. Rule number 2 is only add or subtract like terms. And rule number 3 is that simplifying means eliminating as many terms as possible. Let's demonstrate how these rules work in practice. Rule number 1. Once again, any operation you do to one side of an equation should be performed on the other side as well. Believe it or not, this rule, I think, is best understood by thinking backwards. And what I mean by that is we're going to start with a simple equation and make it more complicated. This might seem counterintuitive, but I'm very hopeful that this will help you understand the underlying concept and set you up for success when it comes to complex simplifications in the future. So let's start small with the equation x equals 5. That's almost as simple as we could get. The only thing that's theoretically simpler would be like 5 equals 5, but that's trivial. Let's begin by stating the obvious. X and 5 have the same value, aka they are equal. If we accept this, let me ask you, what would happen if we added 3 to both of the quantities? Would those new quantities still be equal? It might be helpful in a situation like this to visualize an old-fashioned scale, one that balances by holding a rope or a handle that has 2 weights on either side. Or you might consider a lever that's perfectly balanced at its center, if you're not familiar with this concept of an old-fashioned scale. If the scale is perfectly balanced, what would happen if I added exactly 3 pounds to both sides of the scale? Or if you're imagining the lever that's perfectly balanced, what would happen if I added 3 pounds to both sides of the perfectly balanced lever? Hopefully you're thinking it would remain perfectly balanced, all else being equal. And this is a good physical analogy for how equations work. If we change both sides by the exact same amount with every operation, then we're not changing the relationship between the quantities at all. Yes, the quantities themselves might look different, they might get more complicated, but the fundamental equation relationship at the heart of it, in our case, x equals 5, it will remain unchanged. So with that in mind, let's return to adding 3 to both sides of our simple starting equation, x equals 5. If we add 3 to both sides, then we have not changed the fact that the 2 quantities are equal. We've just made the quantities more complicated. The result on the left would be x plus 3, and the result on the right would be 5 plus 3, which I'll just refer to as 8. So by adding 3 to both sides, we've made x equals 5 into x plus 3 equals 8. One thing that could help deepen this realization is that the value of x itself has not changed. It's still 5. That can help you see that we haven't changed the intrinsic value of anything in the equation itself. We've just made something that used to be simple more complicated. And I apologize if I'm really hammering this point, but I really feel that many people, despite many years of schooling, somehow did not internalize this concept. And it's very, very helpful as a foundational concept because you're going to see some pretty complex equations on test day, probably, almost certainly. And sometimes being able to view them through this simple lens can help not only solve the equations better, but also just help your mindset and help you feel more confident as you do your algebraic manipulation. That's my hope, at least. So let's add a little bit more complexity to build on this concept. How about we multiply both sides by something? In this case, why don't we multiply by 2? So that would give us 2 times x plus 3 on the left side, and then 16 on the right side. We can also distribute the 2 to create 2x plus 6 on the left. So let's do that, and let's say we've got 2x plus 6 on the left equals 16. And believe it or not, the value of x is still 5. And both sides of those equations still have the same value. It just looks more complicated, and it's a little harder to see that original expression. I want to just make a quick side note here that distributing or finding common denominators on one side of an equation does not have to be done to both sides. You might have noticed that in my most recent move. I did distribute the 2 on the left to the x plus 3 in the parentheses, and that made it 2x plus 3, yet we did not do a corresponding operation on the right-hand side to 16. So how does that work? It's because finding common denominators and distributing does not change the value of the quantity. Whereas something like adding 3 or multiplying by 2 does change the quantity. So if we're going to do that kind of operation, the kind that changes the value, that does need to be done to both sides of the equation. So think about the scale analogy again. If I simply rearrange some of the items on one side of the scale, but neither increase nor decrease the items there, then that won't change the balance of the scale. It'll still be perfectly balanced. It'll just look a little different on the left side. But if I add something like 3 kilograms to the left side, I will need to add exactly 3 kilograms to the right side of the scale as well in order to maintain the balance. So you can think of distributing and finding common denominators as just rearranging things without changing the value. And that's why you can often do that to one side of the equation without a corresponding operation on the other side. So just think, if I'm not changing the value of anything, I don't need to do that operation on both sides of the equation. If I am changing the value of something by adding, subtracting, multiplying, or dividing, I'll need to do that to both sides. So what are some other ways that the GMAT could make this type of situation more complicated? Well, we could add in more variables. This is a common tactic because sometimes simply having a lot of variables in an equation can make it more intimidating or more difficult to process for the mind. So let's do something like subtracting a new variable z from both sides. That would give us on the left 2 times x plus 3 if we kept it in the parentheses, or 2x plus 6 if we distribute, minus z on the left. And on the right, we would have 16 minus z. And maybe you can imagine us just going on and on and on and on with many, many, many other operations. We could divide both sides by 4. We could multiply both sides by 10. We could add m times x to both sides. There's virtually infinite combinations of things that you can do to take a simple equation and make it more complicated. But hopefully that helps you start to see how equations can become complex relatively quickly, even if they start out fairly simple. And my hope is that that will inform the next set of steps that we're going to do, which is to use the exact same example to illustrate the concept of simplifying an equation, which is the more common thing that you'll end up doing on test day. And all we're going to do is invert every single step that we just did. So starting with 2 times x plus 3 in parentheses, that whole thing minus z on the left of the equal sign, and then to the right of the equal sign, 16 minus z. And let's just follow the golden rule of equations. Whatever we do to one side, let's also do that to the other side. So let's add z to both sides. That will generate 2 times x plus 3 in parentheses on the left of the equal sign and to the right of the equal sign 16. And hopefully you can already see how that could be really valuable if we were starting from the more complex form. Now we've got a much simpler situation. We just deleted z from the scenario. At this point, we could divide both sides by 2. So let's go ahead and do that. That would yield x plus 3 on the left and then 8 on the right of the equal sign. Now we can subtract 3 from both sides, and bam, we wind up right back where we started with x equals 5. And now we've solved for the value of x. These concepts are the core of simplifying equations, and the idea is we just keep performing the same operations to both sides of an equation until you arrive at the most simplified form. Let's discuss a little bit about rule number 2. When you're adding or subtracting, you want to combine like terms. This is kind of just like a guardrail for rule number 1. You could theoretically say there's only one rule of algebra, which is the golden rule, do unto one side as you would do unto the other. But I like having this rule number 2 here, especially if you struggle with math basics, because it keeps you from doing an operation to both sides that could change the relationship and therefore generate an incorrect answer. So let me give you an example of how that might play out. Let's do x equals 5 again, and then let's say we add 3 to both sides. Like we just did, we should get x plus 3 equals 8, and that works, that is accurate, and that is what we just did. But if I make a mistake, and I think I'm adding 3x to the left side, that would generate 4x on the left and 8 on the right, which is not true. That's no longer the same relationship. Note that if we simplified 4x equals 8 by dividing both sides by 4, we would get x equals 2, which is definitely not where we started with x equals 5. So this reinforces why we do x plus 3 on the left when we are adding 3 to both sides, because x and the number 3 are unlike terms. 3 is not the same as 3x. And that's really an important point to drive home. So consider it this way. We start with x equals 5, and then we add 3x to both sides, which is also a totally allowable move. Then on the left, we would get 4x, because x plus 3x is 4x. And on the right, we would get 5 plus 3x, but we wouldn't be able to make 5 plus 3x any simpler. And it has to remain 5 plus 3x because 5 and 3x are unlike terms. If I made the left side 4x and the right side became 8x, we're changing the relationship. So I just want to reinforce this concept. When you're adding and subtracting, only combine like terms. This is a place a lot of people get into a lot of trouble with. It creates a lot of confusion. So I'm trying to help you clarify it as much as possible. And I apologize if I'm overdoing it. I promise I'm coming from a good place with like the strongest intention for you to have the fastest, best success that you're possibly capable of here. That brings us to rule number 3, which you might recall is simplifying means eliminating as many terms as possible without disobeying the first 2 rules. We kind of already did an example of this as we did our initial simplification, but the reason I like this as a rule, even though technically it's another guardrail, is that it helps people know when to stop, because sometimes it can be hard to know when you've simplified enough, and that can lead to like wasted time if you're just moving terms around but not really eliminating any terms. So here's a quick example of this. Let's simplify 2x minus 7 equals 2y minus 13. Let's obey the golden rule and combine some like terms. And we can start by adding 13 to both sides, because we have some just pure numbers with no variables next to them on both sides of the equation. That's a good way you can recognize what you should start by adding or subtracting to both sides of an equation. So if we add 13 to 2x minus 7, we would get 2x plus 6. And if we add 13 to 2y minus 13, we would just get 2y, because negative 13 plus 13 is just 0. From here, everything's divisible by 2. So we can divide both sides by 2, and that will yield x plus 3 equals y. Now, if you're listening to this on pure audio feed and I lose you with some of the operations because it's hard to visualize, don't worry about that. This is not really about the particulars of the exact equation demonstrations I'm giving you or equation examples. It's more about the basic concepts. If you can come away with the basic concepts, you'll be good, and the episode will have served its purpose. So let's say we simplify this thing and we get down to x plus 3 equals y. At that point, there are no more terms that can be eliminated because there are no like terms that could be combined. So that can't be simplified anymore. Again, rule number 3 is eliminate as many terms as possible, and you could add on a caveat without disobeying the first 2 rules. So eliminate as many terms as possible without disobeying the first 2 rules, and you will be doing all the right things when it comes to simplifying equations. And believe it or not, that is the basics of algebra. That's everything that you would need to know about the basics of algebra. So let's practice one final example to just tie all these things together and hopefully make everything crystal clear. So again, most important thing here is understanding the concepts and how to apply the rules. If you're on the go, just do your best to wrap your mind around the basic moves rather than the specific numbers here. So I'm going to throw a somewhat complex equation at you. Might just be complex because you might not be looking at it, as you have probably been doing with most algebra that you've done in your life so far. You probably haven't done much algebra by audio, but it's the first time for everything. So let's start with an equation, 2 times, in parentheses, x plus 4, and then that whole quantity minus 3. That's what's on the left side of the equation here. And then to the right of the equal sign, we've got 5 times, in parentheses, x minus 2, and then that whole thing plus 7. So 2 times the quantity x plus 4 minus 3. Outside the parentheses, 5 times the quantity x minus 2, close parentheses, plus 7. If you have the ability to write any of this down, I highly recommend that, as writing this kind of thing down accurately is a major cornerstone of success on the exam. Good rule of thumb when you have multiplication happening outside parentheses is just to distribute right away. We talked about distributing in the previous episode, so if you're not sure what I mean by distributing or you want a little more clarity there, I recommend just working through that previous episode right now called PEMDAS and then coming back to where we are right now. If you're ever unsure how to proceed, just follow PEMDAS. Here, we can't combine the terms inside the parentheses because they are unlike terms. We've got x plus 4 inside the parentheses on the left side and x minus 2 inside the parentheses on the right side. So we'll just keep going down the line of PEMDAS, and we don't have any exponents, so we will distribute, which is a type of multiplication, which is the m in PEMDAS. When we distribute the 2 that's outside the x plus 4, that's going to yield 2x plus 8. Then I'm going to distribute the 5 on the right-hand side of the equation. Distributing 5 to x minus 2 will yield 5x minus 10. So now we've got 2x plus 8 minus 3 on the left-hand side of the equation with no more parentheses there. And then on the right side, we've got 5x minus 10 plus 7 with no more parentheses there. Because we have like terms on the left side, let's just combine those first. So let's turn 2x plus 8 minus 3 into 2x plus 5 by performing the 8 minus 3 operation from left to right. Again, just following PEMDAS and the guidelines from our previous episode here. We also have like terms on the right side of the equation. So let's turn 5 minus 10 plus 7 into, 5x minus 10 plus 7 into 5x minus 3 by performing the addition of negative 10 plus 7 from left to right, just like we did a moment ago on the left-hand side of the equation. Now, quick side note here, when you are just adding and subtracting like terms on only one side of the equation like we just did, that's another example of something that doesn't change the value. We're just rearranging the terms that are already there. We're not subtracting 3 from the left side of the equation as a means of simplifying. We're just doing the operation that's already there, 8 minus 3. That would be like if you had 2 pieces of clay on the left-hand side of a scale that are both 1 pound each, and then you roll them into a 2-pound ball. That's not going to upset the balance of the scale if it was previously perfectly balanced. So you can think about combining like terms on one side of the equation the same way you can think about distributing and finding common denominators. It doesn't change the value of the expression. For example, let me just drive this point home. 2x plus 8 minus 3 has the exact same value as 2x plus 5. Okay, so if that was at all confusing there, just put that in the same bucket as distributing and finding common denominators on one side of the equation. Just because I did 8 minus 3 on the left side, which is already written there and is already factored into the value of the left side, I don't need to then subtract 3 on the right side. I only need to do that when I'm artificially adding something that was not there already. Okay, so Now we've got 2x plus 5 on the left side of the equation and 5x minus 3 on the right side of the equation. Here, we can do some simplification because we've got like terms on both sides of the equation. So here, I'm going to use the golden rule. Whatever I artificially do to one side of the equation, I'm going to artificially do the same thing to the other side of the equation. And let's just drive this previous point home here. When I've got 2x plus 5 on the left and 5x minus 3 on the right, and then I decide to add 3 to both sides of the equation to get rid of the minus 3 on the right side, notice that that addition of 3 is not already in either of the expressions. So when you're adding something in or subtracting something away that's not already being added or subtracted in the expression, that's when you need to do it to both sides. If I had 5x minus 3 plus 7 on the right, and it's already equally balanced, and they told me that was the same as 2x plus 5, and then I add the negative 3 and the 7 to make 4, I'm just rearranging the clay on one side of the scale. I'm not actually adding anything to the scale that wasn't there already. So hopefully that's clear. But again, just reach out to us at the GMAT Strategy on current social channels. Give us feedback. If we need to remake this episode to make it more clear, just let us know. Now, in this case, with 2x plus 5 on the left and 5x minus 3 on the right, we could add 3 to both sides, or we could subtract 5 from both sides. And either one is totally acceptable. It's really just about which is going to help you the most in either given whichever situation you're in on the exam. And that's a judgment call that you'll get better and better and better at making in the moment the more you practice. I'm just going to add 3 to both sides just because. And I like to try to avoid negatives whenever possible because I found them to be quite error prone when doing computation by hand. So the result of adding 3 to both sides of the equation would be 2x plus 8 on the left, which is 2x plus 5 plus 3. And then it would be 5x by itself on the right, which is 5x minus 3 plus 3. So that's just using the golden rule. If I add 3 to the right-hand side, then I should add 3 to the left-hand side as well. Let's do a similar move again, because I can see that I could eliminate the 2x by subtracting 2x on both sides. So I'll subtract 2x from the left side, and then I'll subtract 2x from the right side. So I've got 2x plus 8 on the left, I subtract 2x, that just becomes 8. I've got 5x on the right by itself, I subtract 2x from 5x, and I get 3x. So we've now simplified to 8 equals 3 times x. Finally, to isolate x, which is often the objective of simplifying equations, which is also called solving for that variable, which GMAT quant problems frequently ask us to do, we'll divide both sides of the equation by 3. And we'll wind up with 8 divided by 3 equals x. Now remember, like terms are less important when you're dividing and multiplying, so we're not going to worry too much about that. Like terms are primarily important when you're adding and subtracting. That's simplifying an expression. That is simplifying an expression. So things can certainly get more complicated during the exam, and there are definitely a few more tricks of the trade to learn in terms of becoming a master of simplifying equations. But for now, you are all set with the basic building blocks, and you should feel comfortable moving on to more advanced concepts. Now, like I've recommended in past episodes, you can pop a simple prompt into your generative AI tool of choice and ask for 5 examples to help you improve your equation simplification skills on the GMAT. Some type of prompt like that can get you some good examples. But I have not found generative AI tools as of today's technology in October of 2024 to be very good at coming up with GMAT problems on the spot. So I would not recommend using those tools for that. For that, you'll want to get a copy of the official guide for GMAT review, which is published by GMAC and available at MBA.com. Let us know if you have feedback or questions. Like I said, you can reach us at the GMAT Strategy on current social channels. In the meantime, my greatest hope is that this material will make your studies as easy and as painless as they can possibly be. If you want more tips and strategies for optimizing your performance on the GMAT, please head to our website, thegmatstrategy.com, which is linked in the description of this content if you prefer to click on it rather than type it into a browser. And this is a regular show, so please subscribe and please stay positive and stay consistent with your studies. I'll talk to you all soon.